or the very last talk of the day is by Mitali Bafna, and she's going to tell us about unique games and expansion. So take it away, Mitali.
Thanks everyone for coming. Today I'll talk about two joint works. One is with Boaz, Pravesh, Sleel, and David, and then another one which is a follow-up with Dor. Okay, so let's define unique games. We'll look at the special class called affine unique games, in which you're given n variables and two sparse linear equations modulo k, and each equation is of the following form. So the obvious question to ask now is, how do you solve this linear equation, linear system, when it is satisfiable? And we know how to do this by Gaussian elimination. But in fact, in this case, there's a much simpler algorithm. You just do propagation. So create the following graph where you put in a vertex for every variable and an edge for every constraint. Label the edges by the right-hand sides, and then assign the first variable to be 0 and propagate this value to the second variable and so on until you have a solution in k to the n to all the vertices. And from now on, we'll think of this equivalent graph view where we create different unique games instances on graphs by varying the edge labels. So what if I tweak the problem and gave you a linear system in which only 90% equations are satisfiable? Can we find a 90% satisfying assignment, or even just a 1% satisfying assignment? So note that a random assignment satisfies 1 by k fraction of the equations. And here we think of k as really, really large. So this is not good enough. So in fact, in 2002, Court conjectured that this problem is hard. So given 90% satisfiable unique games, finding a 1% satisfying solution is not possible efficiently. And this turned out to have really nice consequences to hardness of approximation, where in many cases, we got optimal hardness of approximation results. And for other problems, these are the best known results, and they are not known under NP not equals B. So what is known about unique games? The history is really like a game between hardness and algorithms. As soon as it was proposed, there were various algorithms that got alphabet dependent guarantees, or like different guarantees depending on the size of the graph, but they were not able to refute the conjecture. And then it was shown that, in fact, unique games is easy on random instances. So where you have a random graph or an expander graph and you vary the edge labels. And in fact, it even had non-trivial sub-exponential time algorithms. So note that both these algorithms are kind of in contrast to hard problems such as 3-SAT, where we believe such algorithms should not exist. And in contrast, it was shown to be hard on small set expanders under a stronger conjecture known as the small set expansion hypothesis, which I will get to very soon. And to culminate these results, unique games were shown to be hard when you have like a 49% versus 1% instance. Yeah, so okay, and so all these algorithms are based on rounding semi-definite programming relaxations, and a specific one's called sum of squares. And today I will tell you about our algorithms that expand the class of graphs on which unique games is easy, while building new rounding techniques for sum of squares. And I will focus on these two complexity results. So these are our results for unique games, and you don't need to know what these classes of graphs are, and I will soon because I will soon define them. So now let me dive into our results. Any questions before that?
So the goal is to guide possible approaches to the unique games. Like if you're constructing it like this, then you want to prove the unique games. Like what's the motivating?
Yeah, that is one goal, and the goal is also to find hard instances of unique games.
If you give algorithms, you're not finding hard instances.
Yeah, I will talk a bit about that in the end.
You know, the too much to other stuff other than this.
Yeah.
Yeah. Okay. So before telling you about our results, let me tell you about this family of graphs, where the vertex set, we've seen this a lot in the program. The vertex set is R-sized subsets of M, and you have an edge between two vertices if they intersect in at least T elements. And this class of graphs is nice because they exhibit all these properties for various regimes of M, T, and R. So you don't need to remember what these graphs are, but like this is just to give an example of all the graphs we will be talking about. Okay, so let's start with unique games on expanders. So we all know what expansion is, and now I'll think of expanders, where G is an expander if all sets of size at most 0.8n have expansion at least 0.2. This is a bit non-standard, but yeah, I could have made this constant a bit smaller, but I decided to stick with the most optimal constant. Okay, so the earliest works showed that we have polynomial time algorithms for unique games on expanders. So let me tell you, let me now give you a different analysis for this algorithm when we have affine unique games instances. So our key observation is that for UG instances of expanders, any two assignments that satisfy 90% of the edges must be equal up to shift on 80% of the vertices. So in some sense, this is a kind of uniqueness of the solution space, because up to there is one true solution and every other solution is a perturbation of this solution in 20% of the vertices. So let's try to prove this lemma. And before that, just this is a reminder. And note that two assignments x and x plus s modulo k satisfy the exact same set of edges. So we'll think of them as essentially equivalent. Okay, so let's try to prove this lemma. And in fact, the proof is not that hard. So create the following partition of the vertices, where for each in each component, so in the 0th component, you put in all the vertices I, where x equals x. So where xi equals xi prime modulo k.
Two solutions, next one.
Yeah, so we fix two solutions that satisfy 90% of the edges, and we want to show that they must be equal in 80% of the vertices. So we have fixed two solutions, and in the first component, we put in all the vertices where x equals xi prime modulo k. And then in the second component, we put it all the vertices where they are different up to 1 modulo k and so on. And now the main observation is that any crossing edge, any of these orange edges, cannot be satisfied by both the assignments x and x prime. So let's look at this edge. So we have that on this edge, you can just subtract both the equations to get that x1 minus x2, if it was equal to a12, then x1 prime minus x2 prime cannot be equal to a12. So now we can use the fact that x and x prime both satisfy 90% of the edges to get that there can only be 20% crossing edges. At this point, okay, so a priori, each of these components could have been n by k in size. and this is much smaller than 0.8n. But now we can use the expansion in the graph to say that at least one component must be of large size. Otherwise, you would have at least 20% crossing edges. So we get, let's say this component was large, so we basically get that x and x prime are equal on 80% of the vertices. Okay, so let's see why this uniqueness of the solution space is even useful for algorithms. And before that, let me tell you about sum of squares. So the sum of squares hierarchy is a powerful meta algorithm based on semi-definite programming. And it's a hierarchy of SDPs graded by degree, where each level takes time n to the d. And usually, given your optimization problem, it's easy to write the relaxation, but it's hard to round the relaxation to a true solution. So and sum of squares captures many important algorithms like linear programming and spectral methods. So sum of squares has been pretty successful in the average case, and especially for robust statistics. And most of these proofs are actually based on uniqueness in the solution space. And in fact, a very strong type of uniqueness where sometimes you even have just one solution. For example, if you thought of the planted clique problem, you have one planted clique, and in a random graph, you want to distinguish it from, and you don't have any other cliques. So these algorithms are based on kind of taking this proof of uniqueness and converting them into an algorithm. But for worst case optimization, very less is known. And this is mostly because uniqueness is too much to expect. So what we do is to relax this to some kind of weak uniqueness or weak correlations between solutions. So now it's actually, we can show it to hold for some worst case problems, but we need some new rounding techniques and analysis. So now we have this intermediate uniqueness where two solutions must be equal on a lot of the vertices, so 80%, but still not all. And now we can use the rounding on degree 2 sum of squares to get a solution. Now let me tell you a bit about the rounding. And before that, let's see the distribution view. So yesterday, Max gave a vector view of that. Let's forget about that view. Think of the degree d sum of squares relaxation as giving you a distribution, the degree d moments of a distribution over 90% valued assignments to your instance. So what do I mean by this? This just means that there exists some distribution out there which is supported over 90% satisfying assignments. And you're given local statistics of that distribution, things like what's the probability x1 equals 0, and then x1 and x2 equals 0, 1, whatever, up to d variables at a time. And this is not actually that, but let's just think of it like that today. Okay, so now let's see what the algorithm is. So now we want to, given the degree 2 moments of a true distribution, we want to actually produce a solution that satisfies 50% of the constraints. So actually our algorithm is pretty simple. What you can do is first condition the distribution over the value of a random vertex. Let's say random vertex v equal to 0. And then once you have conditioned it, you can independently sample from the marginals for the other vertices. And this actually depends only on degree 2 moments, because the second step is you can calculate the marginals of all the vertices, the condition marginals, by just looking at the original degree 2 marginals. So any questions about this? So let's see why this works. So now we will actually use this observation to convert it into an algorithm. So firstly, if every two assignments that satisfy a lot of the edges agree, then of course, if you have a distribution over satisfying assignments and you sample 2 of them, they will also be equal up to shift. This is just like an obvious fact. And now imagine if in fact we had that they agree up to 100% of the vertices, then what our distribution would be, it would just be some assignment x and its shifts. So x plus 1 up to x plus k modulo k, x plus k minus 1. And then it's easy to see why this would work, because when we condition the distribution over one random vertex, your assignment will be fixed and independent sampling will just sample from a fixed value for every vertex. And actually this kind of intuition can be made more robust. And even if you're given equality up to only 80% of the vertices, after conditioning the distribution, you can show that you basically fix most of the vertices up to some variance. So let me give you some idea why it works. So we consider this expression. So this is just expectation of x and x prime drawn independently from the distribution. And this inside quantity is like the sum of squares of the parts that the component sizes that we earlier had. So for example, we proved that one of these parts is at least 0.8 sized. I've just written it as an indicator. So we have that this quantity is at least 0.8 squared. And we can actually rearrange this quantity. This is a strict, like an equality. So if I gave you 2 minutes, you would be able to rearrange this to get this expression here. And now we can see that because we have 2 independent samples and an indicator variable, this becomes the collision probability of the random variable xu minus xv. And in fact, because we have symmetry in the solution space, this is also the collision probability of xu conditioned on a random vertex xv equals 0. So what we are saying is that after conditioning, the collision probability is close to 1. So you are basically fixing the vertices up to this 1 minus 0.8 squared variance. And you can use some simple inequalities to show that this is at most the rounded value plus 1 minus the true value. And we know 1 minus the true value is 10%. So you can rearrange to get that the rounded value is at least 50%. So any questions about this?
I guess it's too fast to follow like this, but your condition on xu and xv holds where u and v are a random edge of the unique game problem.
Oh, sorry. So this expectation is over random vertices.
It's not. That's over all pairs.
Yes, all pairs. So
Okay.
actually, I made the square into an expectation. So
Okay,
yeah,
that is.
yeah. Okay.
So is 50% some kind of variance?
So this 50% is an arbitrary number, but if you actually made this thing 50%, then this analysis wouldn't work, and I will get to that.
In the last equation, like the b is an arbitrary vertex or you
Oh, yeah, okay. Okay, this is a random. So this is the first step of the algorithm.
I see, yeah.
Yeah.
Wait, so the distribution that you get from the SOS algorithm, the expected value is 90%, right? Not, or is it like
Yeah.
every single thing in the distribution has 90%
Yeah,
value?
yeah. So this is actually like, okay, the intuition I gave was for sampling it, but this thing is going to be the expected value when you actually calculate. Like when you do this inequality here, you're going to get an expected value over the distribution. And we know that the expected value is at least the true value because it's an STP.
So if 90% was like 1 minus epsilon and the expansion was good enough, you would be getting like 1 minus root epsilon instead of 50%. Like, do you?
Yeah, I don't think we'll be losing the root, but yeah, yes, I'm just giving an analysis of the previous algorithms. So
So when
those
the
are
clone
even
is
better.
tends to 1, the fraction of constraint that
Yeah,
can
yeah.
satisfy also tends to 1.
Yeah, exactly. Yeah, so when this is exactly 1, you would get back 1. Okay, so let's try to push this idea to a larger class of graphs, and let's go to small set expanders. So small set expanders are graphs where only small sets expand. So we have sets of size at most 10% have expansion at least 0.2. And now we can ask for unique games UG algorithms over small set expanders. And let's try to do the previous, let's try to follow the previous strategy for algorithms. So we can just do the same, we can create the same picture from before, like say that all these edges are violated, etc., etc. But now we can use the small set expansion of the graph to say that because there are only few crossing edges, one of the components must be large. But at this point, we will only get that it's large, it's 1%. We won't get 0.8 fraction. And now we can see whether we can use this observation to get an algorithm. So can we get poly time algorithms for UG over SSE? So it turns out that this is in fact hard under small set expansion hypothesis. So what does this conjecture say? It says that checking if a graph is a small set expander is NP hard. So the Raghavendra-Stoiber result basically says that solving this unique games problem over it should also be hard. So, but what if we relax to graph where checking this property is easy? And this is what we do. So we get algorithms for unique games instances over these checkable small set expanders. And it turns out that, in fact, all the graphs we know of are also checkable. And this is because the way we prove that they are small set expanders, the proof itself gives us this checkability property. And all the proofs we've seen in the, just to give you an idea, all the proofs that we've seen so far are checkable, probably not the stochastic calculus proofs, but yeah. So now we can use this checkability property, but now round a higher degree sum of squares relaxation to get a solution. Now let me tell you a bit about the rounding.
Just a quick question. Why is checkability important here? So if you know that, if you were promised that you have a graph that is a small set expander, you wouldn't be able to solve this in polynomial time. Like you really need to know to have an algorithm. You need to know how to check the unique.
That's
like,
because,
for example, for the expander case you were talking about, you don't need to check if it's an expander for it to work.
yeah, so there actually we use the fact that Cheeger's inequality always gives us this checkability.
Okay.
Yeah, so whenever it's an expander, you have like the easy direction of Cheeger's inequality. This property. And yeah, the point there is that sum of squares has to know about the expansion. Yeah. So the proof that we did. Okay, so we can again try to do the same analysis of this algorithm. But now the issue is that we only have 0.01 here, 0.01 squared here. And whereas this 1 minus 2 value is something like 0.1. So this inequality, this gives you a totally like stupid bound on the rounding value. And this is completely useless. And intuitively, this is because when you say that two assignments are equal in 1% of the vertices, these vertices could be the ones where x and x prime violate all the edges. Because we know that 10% of the edges are violated, so these vertices could have all the violated edges touching them. And this is not something useful in that case. So now what we need to do is that we need to show that x and x prime actually agree in 1% vertices that also have high value. And then we need to like generalize, like kind of build upon this analysis to round, to show that this algorithm works. And this process actually requires higher degree moments and higher degree SOS. Okay, so I won't tell you about this, but let me go to a larger class of graphs, globally hypercontractive graphs. Okay, so this is a totally unoriginal. So now, what if your graph had small non-expanding sets? Can we still? Yeah, so this is something we've already seen umpteen times. And this result shows that this particular noisy Johnson graph is a sausage. So there exists a small collection of small canonical non-expanding sets in this graph, such that every non-expanding set, such as this S, must be close to a union of canonical sets. So we have that S must be basically a union. So the only way to form these sets is by taking unions of the BIs. So now we again have this picture for the 10th time. And in fact, this claim is no longer true. So we can even provably show that weak uniqueness fails. So two assignments, x and x prime, that satisfy most of the edges might not agree in 1% of the vertices. But at this point, we can use global hypercontractivity to say that this partition, because it is non-expanding, it must be of this form. Okay, so now so how should we use this picture now? So now what this says is that for every two assignments, x and x prime, satisfying a lot of the edges, there exists many canonical sets, BIs, such that x and x prime are equal in 1% of the vertices of BI. So here I'm just taking all of these sets, and that's why I have many. And inside them, you can see that they completely lie inside the partition. So that's why x and x prime are equal on them. Okay, so because we have this for all assignments, we also have this for distributions over assignments. And now what you can do is that given a distribution, you can exchange the quantifiers. So given a distribution, you know that for every two x and x prime sampled from them, you get that there are many canonical non-expanding sets for that x and x prime. So you can exchange the quantifiers to get that for a fixed non-expanding set B with large probability over x and x prime, they are equal in 1% of the vertices. And this in some sense says that for a fixed set B, you have only a few solutions on B. This is because otherwise you wouldn't have such, you kind of have only 10 to the 10 solutions. So if you apply the small set expansion analysis with some more care, you can actually get this valued solution. But this is not good enough because in general, this value could actually depend on the alphabet size. When you take Johnson graphs in particular parameter regimes, this would depend on the alphabet size, and these are the Johnson graphs that we are interested in. Yeah, so this is something like k to the minus 10. Okay, so let's see how to round this. Okay, so the obvious solution to round this would be to condition the distribution, the D cross D distribution over x and x prime, on the event that the assignments are equal on this fixed set B. And then once we condition, we would have just by definition, we would have that x and x prime are equal up to 1% on B, and then we can apply the small set expansion analysis from before. So any questions about this? Okay, so the issue is that conditioning actually destroys the independence between x and x prime. So in particular, the event you conditioned on could just be x equals x prime, for example. And then by definition, x and x prime are correlated. So you run into this loop where you want to, so initially recall that we want to pick two random assignments from the distribution and say that they are correlated, and that's why the original distribution had large collision probability. But after you condition, they could literally be equal, and that the two solutions being correlated does not tell us anything about the original collision probability. Okay, so our main fix is to pre-process this distribution D cross D so that even after conditioning on high probability events, most of the vertices XU, most of the pairs of random variables remain independent. So yeah, this is just some lemma about distributions. So any questions about this?
Your small probability here is like
10. Yeah.
Then what happens to checkability? If you look at the fact that you have this explicit list of small set, bad sets.
So basically this proof of uniqueness always uses checkability, which I was hiding under there. Yeah. So I can tell you a bit about what this pre-processing is. So for example, if the event E you conditioned on set a lot of the vertices to be equal, we kind of, because you condition only on 1/10 to the 10 probability event, it cannot set many of the vertices equal. It cannot set like n vertices to be equal unless they were already equal to begin with, unless your distribution was literally one assignment supported over one assignment. In that case, conditioning will obviously set, you can condition on a half probability event and create correlations between x and x prime. So the idea is to remove the original correlations that existed in D by doing some kind of global correlation reduction. And then whenever we condition, we retain pairwise independence. Okay, so then we can use this all this machinery to get 1% satisfying solution. Okay, and we've already seen that many graphs satisfy this this kind of property, in particular Grassmann and noisy walks on the Johnson and high dimensional expanders.
These are like checkable, like these curves are checkable.
Yeah, so it requires some work, but mostly the intuition is that they only use, so all these proofs are like polynomial inequalities, like for example, Bonami's lemma, and they only use obvious facts such as Cauchy-Schwarz and Holder.
Process it uses fixed distribution, right?
Yeah, so D is some distribution outputted by the SDP, and then we can do whatever we want on it and then output a solution. So what we do is do this global correlation reduction. Yeah, so okay, this global correlation reduction is like a particular operation. You basically condition on a lot of vertices until the remaining distribution has no dependencies, like XU and XV are almost pairwise independent. Yeah, then we run the previous analysis on time. So now what about non-globally hypercontractive graphs? In particular, let's say the Johnson graph in this regime where it's not globally hypercontractive. So here we actually think that we should not have algorithms, and that's because of this 49% versus 1% hardness result. So this is because these hard instances are of this form. So they are something like the Johnson graph in this parameter regime composed with the Grassmann graph. And our algorithms work, even though I did not show you, they work in this 49% regime also. So basically, at a high level, this tells us that this graph is easy, so this graph must be hard. And a caveat with this thing is, yeah, so this is likely hard. And I think a small caveat is that our algorithms work for affine unique games, and this reduction produces general unique games. And if we ran the reduction from well-known reduction from general unique games to affine unique games, yeah, so we are not sure whether it destroys this global hypercontractivity property or not. So so we know already that like the algorithms there are expander algorithms from previous works over general unique games. And we think that, I think even the small set expander algorithms work over general unique games by just running the reduction. But for these globally hypercontractive graphs, we might destroy the property, although we think it should hold for general unique games. So up to that, this is kind of some evidence that this Johnson graph in this parameter regime should be hard for unique games. Okay, and this is a summary. And now let me conclude with some future directions. So one of the main open questions is to get hard instances for unique games or integrality gaps. So on the Johnson, okay, this is, I think this is cut out here, but here I had 49% satisfiable. Oh, okay. Yeah, so on the Johnson graph in this 49% satisfiable regime, when we look at expanders and small set expanders, etc., these things are easy because of algorithms, and this is likely hard because of the reduction. But in the 99% regime, our algorithm still stops working in this same regime of parameters. So a natural question to ask is whether we can build integrality gaps using the Johnson graph. Okay. And then I showed you some rounding techniques where we take proofs of uniqueness into and get a solution. So it's natural to ask what are the other optimization problems with such uniqueness properties. And by uniqueness here, I again mean that where two solutions to the problem must be correlated in, let's say, a small constant fraction and not really like 90%. And even in our algorithms, most of the work goes in showing such uniqueness properties. So yeah, it would be nice to see what other problems have these properties. So this is the picture of the hard optimization problems from earlier. We have a lot of algorithms now for unique games, but all these other problems, we basically know only one algorithm, which is taking the degree 2 SDP and running some kind of simple rounding on it. So basically, it would be nice to see if any of these techniques give new algorithms for these downstream problems. For example, can you build better sub-exponential time algorithms for any of these problems like max cut? Or can you bridge the gap between hardness and algorithms for these problems where there is a huge gap? Okay, thanks.
Any questions for Mitali?
Wait, so what parameter regime is the Johnson not globally hypercontractive?
Yeah, so that's in the regime where you have n, like n is growing and k is a constant. Okay, so I don't. Okay, so you have n as the universe size and k is a constant. But k, think of it as a large constant. Think of it as literally, let's say, the alphabet squared, like the alphabet size squared. And then you connect two edges if they differ in. Or you change, to connect two edges, you change 1 by k fraction of the coordinates. So you change very few coordinates. That's right.
Yes.
Also, basically, where the noise is dependent on the alphabet size.
Any more questions? Okay, so let's thank Mitali again. So see you all tomorrow.